Hi, my name is Sydney Dolan, and today I'm going to be presenting on SunE, a dataset and benchmark for event-based sun sensing. Now, I come from an aerospace background, so I'm particularly interested in computer vision techniques for space applications. One of the biggest uses of computer vision on satellites is in attitude determination, which is figuring out a spacecraft's orientation by observing astronomical objects. Among attitude sensors, sun sensors are the most widely used. And this is because they're simple, low power, and the sun is almost always visible in space. Sun sensors work by estimating the direction and the position of the sun relative to the spacecraft, as shown in the figure on the right. Event cameras are especially promising for this task because they have a very high dynamic range. This means that they can detect both extremely bright and extremely dim objects, which is critical in space environments that often have extreme lighting contrasts. Because of this, one of the first directions we decided to explore was using event cameras for sun sensing. Unlike conventional cameras, which can saturate or even be damaged when the sun is in frame, event cameras are rated up to 100,000 lux, making them well suited for this application. Now, the performance of sun sensing in conventional cameras has plateaued, and this is in part due to a phenomenon known as the S-curve centroiding error, as shown in the plot on the right. When a point source function is at the center of a pixel, the resultant centroiding estimations are very accurate. However, as it moves from one pixel to the next, the point source function spreads. The algorithm, due to the sample resolution of the available pixels, starts to bias the centroid fit to the starting pixel. This creates a systematic offset. The measured position lags behind or jumps ahead of the true one. As a point source moves from a perfect fit in one pixel and then on to the next, the resultant centroiding estimation produces this S-curve-like error, where on the boundary between two pixels the error is the largest, but as it moves towards the next pixel, the centroid error decreases. The time dimension of an event camera can add another dimension for signal accuracy to address when the star or sun is near pixel boundaries. To evaluate event camera sun sensing capabilities, first we had to collect data. So we went to a sun simulation facility that had a 1.1 AU sun simulator. And this is important because the solar intensity experienced by satellites is more intense than what we experience on the ground. So we went into this formalized testing facility and generated a data set where the event camera system was facing the sun, with the sun passing in view at different relative angles. Some videos from the associated data set that we've created are shown here. For each scene in the dataset, we provide the following annotations: the centroid of the circle and the radius, as well as the centroid of any optical artifacts in frame. So on the right side of this frame in this screenshot from the dataset is something known as a ghost, which is a secondary mirror reflection. And this is caused by the interaction between the incoming light, the lens on the system, and the event camera. So we provide these annotations in the dataset along with the camera intrinsic matrix and associated calibration information. Another phenomena I want to call out in this screen capture is the absence of events in the center of the centroid on the left. This is referred to as something called the black sun effect in sun sensors, which occurs when the light of the sun saturates the pixels, causing them to create something like a black sun where they don't report any events. While this is well documented in conventional cameras, something exciting that we learned about during testing with this camera is that you can also observe this phenomena with event-based systems. So using this data set that we've collected, we then proposed an associated benchmark for event-based sun sensing. And so in our benchmark, first we collect all events from a short time slice in the observation recording. Then we generate an event frame using only all of the positive events within this time slice. The reason we only use the positive events is because they're indicative of changes in brightness, and thus the best indicator of the current direction of motion. Using this positive event frame, we then apply a contour detection algorithm to find significant contours in the image. We score these contours based on the centroid event density, the arc density, and the Kalman tracking penalty to ensure consistency across results so that the solutions don't largely skip to an area from where they were historically. On this slide here, we have an example of the performance of the algorithm where the true centroid is in green and the estimated centroid is in pink. Across all of the scenarios evaluated, Our approach resulted in a detection rate of about 95% and achieved roughly coarse sun sensing accuracy. And so future work from our proposed algorithm, we're really interested in exploring more on this stray light mitigation effect. We've captured a lot of interesting optical sensor interactions. There's also certainly more advancements that could be made to incorporate more high fidelity tracking and event-based detection techniques. And also we believe this data set will help others interested in synthetic event generation and how we capture modeling stray light effects into the sensor plane. Thank you for attending my talk, and my contact information is in the details of this video.